now. Okay, now welcome folks to the Triton community meetup. Our first presenter today will be Hong Tao Yu from Meetup. Hong Tao, would you like to take it away and talk about some work specialization work you're doing?
Cool. Are you seeing the presenting view?
Yep, we're seeing the presentation view. It looks good.
I see. Now it works this time. So cool. So yeah. So hello everyone. Thanks for being here. I'm Hong Tao from Meta, and I'm gonna share some update from for the Meta's recent work on work specialization. So this is roughly the outline today. We're gonna start with current status, performance numbers, and introduce the work specialization concept, and then the compiler implementation. And at the end, we'll be doing some case study. And I think Mama and Kevin will be joining us for the case study. So the current status is work specialization is available to PyTorch users through PyTorch 2.6, and that is with Triton release branch 3.2. And then we're also working on making it available through release 3.3. And it's currently only targeting NVIDIA Hopper, and we are working on retargeting the NVIDIA Blackwell platform. And we're also working with upstream to integrate into the Triton. That's going to require some refactoring based on the recent newly introduced work specialization operations. And we are still working on supporting more complicated kernels, extending the features on our end. So for the performance wise, we got the Meta's IPA row-wise gem case working, and with work specialization, we are achieving like 3 to 5% performance gain over the high performance 1D persistent loop Triton kernel. And for flash attention, we are also achieving pretty good results, and about 10% to 15% improvements. And this does not include the perf can go higher. So this is only with work specialization, does not include any computation pipelining and ping pong work we are doing as well. So the main benefit of work specialization is to improve instruction level parallelism. It provides some improvements on top of the hardware instruction scheduling support, and so because the hardware doesn't, the dynamics instruction scheduling isn't really as powerful as on the CPU side, so the compiler needs to do a better job here. And the work specialization leverages the multi-way work scheduler that can allow you to run multiple works on a single core, but targeting different function units like memory function units, ARU, SIMD, and the tensor core. They can run in parallel, so we are able to make the work run parallel on top of that. And it's a bit different from the classic instruction scheduling or software pipelining, which targets mostly the inner warp scheduling scope. And warp specialization is more like a cross warp, more multi-threaded way scheduling. So let's take gem as an example. And without warp specialization with uniform warps, so we'll typically have 8 warps doing the gem problem, where 8 warps together collectively solve compute the output tile of m by n shape. And each warp is gonna be responsible for loading 1/8 of the data. And we divided the 8 warps into 2 groups, and one group is responsible for half of the output tile. And yeah, so as you can see, every warp runs exactly the same instruction stream, and those instructions and barrier and the MMA instruction. And this model is quite effective for gem kernels, which is relatively simple, but it might be challenging to go with a more complicated kernels where have multiple load and multiple MMAs, and how to schedule, when to schedule, how to reorder the instruction sequence is going to be a bit challenging there. And you're going to compute the right timing for instruction to be issued when they are ready to be issued. And with warp specialization, we are generally simplify this problem by separating operations with specific function into different warp scopes. And here we are going to use one more warp group, so 12 warps in all. And 4 warps will be responsible for producing data. They usually called producer warp. And the instruction stream there is relatively simple. They just do load and the continuous load without varying, like how do you reorder instruction, schedule instruction, then mix with other instructions. And the consumer groups are also very simple. So they keep doing MMA, and until they run out of data, right? So, and yeah, and there are some simple scheduling done here in the producer world, like we can compute the timing and to just unblock the consumer once its data is immediately available. So, and yeah, so we can, on top of warp specialization, we can still do scheduling like for the consumer warp when the kernel goes complicated, like with flash attention, you would have other non-tensor core operations in consumer warp. You can still do computation pipelining there. Yeah. So enabling WIS is quite straightforward. We are taking an automatic approach. So you just need to add a couple of switches to the auto-tune config. And here we are specifying how many consumer groups we'll be using. For the jam example, we'll be using 2 groups. And the number of buffers between for data transfer between producer and the consumers. So 3 here kind of mimic what NumStage 2 do is going to use sorry, it's a bit different. It's going to use 3 buffers between producer and consumer. So our implementation is mostly based on a async task concept. We are abstracting a specialized warp to be a kind of task, and the task can run in parallel simultaneously with other tasks that doing a different job, so they do not compete the underlying hardware resources. And tasks communicate through with each other through barriers in shared memory. They also share data through buffers in shared memory too. So if you think task 0 is producer task, it's going to produce its data into the shared memory, and the consumer task is going to fetch the data from there. And the barriers is more likely for synchronization or communication. And on the bottom, the one task will be typically mapped to a work group which has 4 warps and 128 threads in all. This is for NVIDIA platform. So our implementation in the compiler has multiple passes, and we started from an automatic task partitioner that can identify some heavy computation ops and partition the program into different regions conceptually. But then on top of that, we are doing the data partition, like for same code region. If we really want multiple tasks to run that, we need to figure out which part of data they are going to work on. And also the producer consumer, we're using multi-buffering. We support multi-buffering so that the producer does not have to be necessarily blocked by consumer. It can move forward with additional buffers. And yeah, synchronization, primitive operations placement, and actual code split and lowering is pretty much the infrastructure we were building. And yeah, let's take an example and see how those works. So I'm having the source code here, but keep in mind everything happens really on the TTGR level. I'm using the Python code here for easy illustration. So yeah, so this is a jam K loop. And the automatic task partitioner starts with funding the operation, heavy anchor operations like load and the store or dot operations. And it annotates this thing program based on a cost model, and it figures out what the task is the operation should be included into. So for example, here we are using task 0, which is always the producer task in our implementation. And for load and for dot, we are giving it to consumers because based on the shapes, right? So, and yeah, stars we in this model is in the same group with the consumer with the dot operation. And once we figure out the anchor ops, we are gonna propagate the anchor ops, the task ID of anchor ops into the whole program. And yeah, so through dependency chains. And for data dependency, for example, like the opposite is gonna be used in producer, the consumer group, and its initialization is also gonna be in the consumer group. And for control dependencies, like the for loop is going to be used by all the tasks. So up to here, once we figure out this, every op should have a task mapping, and yeah, and after that, because we are using the two consumers mode, is well known as the cooperative partition mode, because we see opportunities there, because yes, it depends on the tile size. And now the data partitioner kicks in, try to figure out how do you share data between the two consumers. And here we are gonna split the dot operation into two, and one which is each of them is responsible for computing a partial tile of the output. So here we're going to use two consumers, so one computes the upper tile, one computes the lower tile, and the load is going to be split as well correspondingly, and also the star, right? So the whole program is going to be partitioned into two independent tile computation. And yeah, so the final step is, well, it's not really final, but the last step is to continue partition the program, split the program into different pieces while adding the synchronization primitives. So here we are using 3 regions, for one region for each task. So we have one producer task, two consumer tasks, and they talk to each other, they share data through each other. And on the producer side, the control dependency is shared with the consumer, is exactly the same. And the producer starts with a synchronization called producer acquire. So it's trying to acquire the buffer, and once it's acquired site, it fills buffer with the data, and then it tells the consumer that the buffer is ready through producer commit. And for similarly for the other two data sources. And on the consumer side, it's trying to acquire the buffer once it have data there ready, and it's going that through the consumer wait primitive. And once it gets its data, it continue the computation, and the computation is done, and it release the buffer. Then it back to the producer. If the producer is still for the second loop-iteration, it needs to wait for the consumer to release. And once the consumer is released, and it continue populate the buffer with new data. Yeah, so we should have already covered this 4 very basic primitives. And we can do some slightly advanced instruction scheduling to compute the right timing, so that the consumer will be unblocked when the data is immediately ready. So in that sense, because the two consumers share the B tensor, right? They compute upper C, lower C, but they share B. They use upper A and lower A respectively. So now here we do some scheduling. We allow B load happens first, and upper A happens second. So at this point, after the both load is done, a consumer 1 can be unblocked immediately, and then producer continue loads the lower C, and the consumer 2 will be unleashed once it's done. So multi-buffering is also supported. Like if it's one buffer, the producer is gonna wait until all the both consumers to finish consuming it, right? So it cannot move forward. With multiple buffers, it can continue populating the second buffer, third buffer with additional tiles, with new tiles. And it's kind of like in a rotating way. This is very similar to what the current software pipelining does. And the barrier is going to be having multiple copies as well. One corresponds to one buffer. So we are still working on some advanced supports, like multi-buffering through multi-dimensional loops, and buffer sharing across regions in one group. And we are seeing very complex control flows with our customer. You have kind of conditional statements in the loop, and how to figure out the update of the barrier and buffer indexes is not trivial. And also the cooperative partitioning is very classic. We are seeing a need of additional different partitions, like ping pong partition on the loop level. If the epilogue of loop is really long, and you want to overlap it with the whole K loop, not just the one last K loop iteration. And there's other partitioning mode like that's needed on the new platform, the Blackwell platform. And also our task partitioner is not really powerful these days, and we need to enhance it based on some precise latency modeling. Yeah, I think I'll switch to Mama and Kevin for a case study of the flash attention. Are you here, Kevin?
Yes. Yeah. So we want to know what actually happens for flash attention, and so this is actually a quite ancient prototype for profiling the intracranial behaviors, and things get massive improvements in the open source Proton dev, but nevertheless, this can deliver already some insights about performance. The figure here, it's about the flash attention tutorial example, and we can see there are so it's organized as thread blocks, and each thread block has 2 work groups. Each work group has 4 warps, and so there are multiple iterations, and in each iteration, I divided it to 5 regions, like bookkeeping, issue the first gem, softmax issue the second gem, and asynchronous loading tile. So the interesting thing here is there are 2. So the example leverages the async copy and wait group, commit group, wait group synchronization primitive. So there are 2 places between region 1 and region 2, and region 3 and region 4. So that means at those points, all threads in the thread block, they will get synchronized. So as a result, you will see the things almost aligned, right? So there is almost no interleaving, which is not ideal. Ideally, you want things get interleaved while you're doing tensor core, the other guy is doing the other work group doing CUDA core stuff, right? So that's how you make sure your hardware components get utilized, especially for those low occupancy stuff, like each thread block takes a bunch of resources, like shared memory for buffers, and the old philosophy of GPU is like you have a bunch of those thread blocks in the same SM and get scheduled by the hardware scheduler to overlap those stuff from the hardware. But as long as you have a single thread block, it's things sitting idle. So for here, the SM here, most of the time it's idle. So there are a bunch of opportunities to improve that. Next slide. So actually with MEMS, like flash attention optimization, we can see that here are 3 work groups, 1 producer work group and 2 consumer work groups. And you can see a lot of interleaving happens. Most interestingly, in the gray boxes, it's overlapping with TMA and the CUDA code. That means the TMA actually frees the CUDA code doing some actual useful computation rather than some stupid data movement, right? And the next thing is the red blocks. It's the overlapping between it's interleaved. So the things, the CUDA core computation and the tensor computing, they are overlapped. And the tensor core and actually the CUDA cores keep issuing instructions while CUDA core is executing. So combine these 2, like gray box and the red box, you can see a lot of overlapping, or a lot of interleaving here. And you can see that there is a boost for SM utilization as well as the compute throughput. Yeah.
Yeah, I will just go quick. Yeah, so because we're running out of time. So yeah, this basically like flash attention with data partitioning that Hongtao mentioned, like a cooperative data partitioning. So yeah, so basically like we have we have different queue and then the same KNV, and then the two consumers take the same KNV from the producer. Okay, and next slide. Yeah, so basically, in order to achieve performance like on par with FA3, we need some other optimization like computation pipelining or better software pipelining plus ping pong. So that's like the left column is like what we emit with warp specialization, and then the middle one is like what we want with computation pipeline plus ping pong. So what you can see, just like we need to shift the first gem out. So they will have a one iteration difference between gem 1 and gem 2. So they are in different software pipeline stages. But when doing this, we need to make sure the consumer wait and the consumer release, they're the dependency with the gem. So you can move them together with the gem. And then we also need to do ping pong. Ping pong is like, just like a barrier, a named barrier pair that so you force. So it has a critical region. So only one consumer can be in that region. So all these optimizations are kind of like preliminary versions are kind of I think in Facebook experimental, but we're still like finalizing and then trying to publish later on. Yeah, that's it.
All right. Well, thank you very much, Manon, Hongtao, and looks like Kevin. I'm going to add you back here to the stage. We have like 2 questions that'd like to be asked. Jaime or Jamie, would you like to ask your question, or would you like me to ask it for you? Give me 1 second to ask. Otherwise, I'll ask it. First one is, Jamie asked, is there an equivalent warp group in AMD GPUs, and does this apply to AMD GPUs?
That's a very good question. Actually, yes, we are doing that for AMD. There isn't a concept of group when you think of barriers. So there's no name barrier that you can use to communicate within just 4 warps and between a fixed number of warps. So, but we are simulating that. We are using the shared memory atomic and add to simulate the shared barrier support on NVIDIA. So we are achieving that same effect on AMD.
Okay. And we have a second question also. Would it make sense to promote some of these controls to the right level in Triton, height level in the Triton language for more complex algorithms, patterns that the compiler can't detect automatically?
Yeah. Actually, we started from there. So we have extended Triton DSL to allow users to annotate their program with their partitions they want. So the TL async task concept is introduced in our Facebook experimental branch. We are still balancing that, but as long as we get enough user decisions, we can try to automate that and see whether automation is possible here.
All right, excellent. Thank you very much. All right, so next up, please raise your hand if you are the people who are going to give you talk on the AMD update. Who's talking about AMD update? Please unmute yourself and I'll let you take the stage. Does anybody know who's giving the update on the AMD update? Otherwise, we will skip and we will head to the number 3 topic. AMD one more time? Nope. Number 3 topic is shared middle layer update from Microsoft. Waiting for somebody to start presenting if possible. Okay, does anybody know who is going to give the shared middle layer update from Microsoft? No? All right, so this might end up being a little short of a meeting. So I've got the 4th topic, which is questions from the Intel team. Do you have anybody from the Intel team? It's not working. Are you seeing any pings? By the way, if anybody knows who these folks are, if you could ping them on Slack, I can add them by getting some folks to possibly drop off. We have a limit of like 15 people. Do you have? I've got Minjiang over here. Minjiang, did you happen to see anybody on like Slack like saying like because I couldn't get in?
No, there is no any. Yeah, if you have any joining, yeah, there is no any update from the AMD Microsoft. So yeah, I don't see any ping in Slack as well.
Yep, I don't see anything in Slack either. All right, so other than that, I will open up the floor to anybody. Oh, somebody just said yes in the YouTube comments. Give me 1 sec. I will need to have one person, Nat. Oh, Nat. Okay, Nat, thank you very much. I'm going to add you to the stage, and if you've got a presentation, I will let you go.
Can you guys hear me?
Yes, we can hear you.
Interesting, because I did say something before, but I don't know if that went through.
Yeah, I think you were muted earlier, or at least that was partly. So if you've got a presentation, please start sharing it, and I'll put it up.
Yeah, sounds good. Give me 1 second. Okay. Can everyone see my screen? Okay. I think yeah. Okay. I'm gonna start. So hello everyone. My name is Nyat. I'm currently working on the Microsoft Maya compiler team. Today I'm gonna give a short update on the current state of the Triton Share project. Before going into more details, because this is the first update on TransShare, I'm going to give a quick introduction of the project for people who are not familiar. The project started out as a way for our compiler team to quickly support Triton as a front end. We already had an MYR compiler at the time, so the quickest way to bring up our compiler to support Triton is to have a middle layer that converts Triton IR into MYR core dialects. The benefits of using MYR core dialects is any Triton programs that Triton Share can lower will be able to run on the CPU using just core MYR to LLVM conversion passes. The core part of the project is an analysis that detects contiguous memory accesses. This is particularly important for AI accelerators. For example, Triton loads and stores lower to static memory of copies. This analysis is similar to access info analysis in Triton, although we started looking into more detecting more types of pointer sequences. And finally, the project is open source. We do all of the development in public. We also try to keep the project in sync with Triton, although progress might be slow sometimes due to priorities. So that's a quick overview of the project. Now I'm going to go into the updates and the progress we made over the last year. The biggest one being a rewrite to make the compiler passes more modular. This came from Meta. I'm going to transition to Haishan, who will be representing this slide.
Yes, thanks, Nyat. And hi, everyone. My name is Haishan. I'm a software engineering manager at Meta. We've been collaborating with Microsoft on Triton Shared. Yeah, as Nyat mentioned, we made some good progress last year on restructuring the compiler passes. The main goal was listed on slides. We want to decouple the extraction of structured memory access information from the actual lowering of the IR. And we also want to allow more customized lowering flow in the end-to-end compilation. And the last goal is we want to have a more robust behavior on analysis failures. For example, when we cannot, convert, a memory access into a structured memory access. So the work that we did is we essentially broke a single monolithic, which is in a quite complicated compiler pass into 3 separate passes that are listed on the screen. And just to give a better feeling on, what we are doing here, there's a very short example at the bottom. There's a sequence of operations that convert or rather creates a tensor of addresses. And this is probably familiar to most of the people on the call. What this pass does, and specifically, after this restructuring, what the first pass does is it essentially converts all of these complicated memory addressing patterns into a single operation and explicitly describe what's the base address, what's the stride, what's the offset, and so on. And that gives the compilation more flexibility in lowering those into higher performance memory access. And that's my slide. Back to you, Nyat.
Yeah. Thanks, Taishan. So that was a great update. It makes it easier for us to add more improvements to the passes. So during last year, some of the improvements we made are improvements to our pointer analysis. This is built on top of the rewrite that Haishan did to support nested loop and other pointer sequences that are seen in production trend kernels. We also started having a limited support for lowering non-contiguous memory access. And thanks to the community, we also have more op supports as well. And in terms of the upcoming work, some of the work that are in our roadmap is to have complete fallback support for non-contiguous pointers. This is a change that's going to require the pointer dialect to land in MIR first. We also want to detect more memory access patterns. The ones we're looking at are row gather and row scatter. And finally, we want to improve the paths to support IRs with control flow ops, such as SCF IPS. So that's it for our updates. Thanks everyone for your time and support. I'm sharing the GitHub link here again for folks who are interested. Any contributions and ideas are welcome. Thank you.
All right, thanks, Nat. Are there folks who have questions or things you'd like to ask Nat about their shared implementation, or also for Haishan? And you can unmute yourself, and I'll let the audio come up. Or you can also put it in chat too. And I think Lucas says he knows somebody from Intel who would like to join. Lucas, if you can, just give them the link. I think we have room for like 1 or 2 more people to actually join. They should be able to rejoin them. What questions? I'll toss one out there because that we don't have anybody else asking questions. What are your future plans, I guess, Haishan and Nat, in terms of like additional things that you see that could be broken down and using your decomposable methods? Are there other things that are that you think are high priority that you would like to actually start moving over?
Yeah, I think I can go first. One of the things that stood out for us at Microsoft, the kernels we've seen are, not all trend programs will have patterns that can be detected in improvement to be contiguous. And so right now, particularly for Microsoft, we don't have way to completely fall back into a mode where we have complete gather scatter support. So that is something that we mentioned in the slides where we'll kind of trying to wait for the pointer dialect in the MOR project to land before building on top of it. And other things, right now for pointer loads of like say an n by n loads of stores, pointer analysis will not will fail if the loads are not entirely contiguous. And so patterns we see are, even though the loads are not fully contiguous, some of the rows are actually indeed contiguous. And so we can split the load into multiple chunks of contiguous loads. And so we call them row gather and row scatter. It's just some of the things that are important in our short-term roadmap right now.
Okay, and Haishan, sorry for leaving you off there. Let me just unmute you.
No worries. Yeah. I guess adding a bit to what Nyat had mentioned, especially after the rewrite that we have done, in cases where, you know, the pointer analysis cannot extract information, we do leave the IR intact. So, you know, any existing passes that people have in, you know, dealing with those unstructured memory access will still be able to apply. But, you know, as Nya mentioned, that there could always be optimizations on, you know, row gather and so on. One more thing that I want to mention is also, you know, we went through quite a bit of effort to make sure we can do this rewrites when, you know, loops iterate on tensors of pointers, which is a common pattern we have observed in a lot of the Triton kernels. With more complicated kernels, what we see is also that there are, you know, if-else ops, for example, being used in, you know, producing these tensor pointers. We kind of see it as a relatively low-hanging fruit to support those, but it will, you know, significantly improve the coverage of our analysis. So that's another opportunity.
Excellent, great. Do we have some other questions? And while we are waiting for other questions, if I have folks from either AMD or Intel who would like to present, please ping me in the private chat channel, and I'll make sure I get your presentation up. Okay, Jianhui. Give me 1 second.
Okay.
All right, Jianhui. Let me get the other folks off the stage, and I will let you take over. Do you have a presentation you'd like to give?
Actually, I don't have presentation. I just have two high-level questions. So, so actually, I missed the initial part on the warp specialization. So, at the high level, we really want to understand that, like, what kind of technique people should, as a backend, should develop the first. Like, should we try to enable, so for example, like a warp specialization or software pipelining? You know, like from your experience, like which one you see is a priority for Triton? Like which lowering is preferred based on your experience, and like are you progressing, like try to bring this warp specialization to main, and then like for example on NVIDIA device, which one will be the main lowering?
Yeah, that's a very good question. I see they are not mutually exclusive. So but the order is still needs to figure out ordering, the past ordering. But I think on H100 we could do WIS first. That leaves that pulls the producer ops out of the consumer, the original program, right? And leaving a only consumer only scope for pipeline. So we can still do software pipelining there after the loads are moved out. And on B200, we are not sure. We are still in discussion, like with upstream. Aman, do you have any?
Yeah, I think kind of agree. I think initially one of the benefits of warpization is like the outer loop software pipelining was not working as we like, but then there have been improvements in that in OSS. But then the other side of the warpization is like either overlapping of tensor core versus CUDA core, I feel. Like you can like ping pong and then control which one goes to CUDA core, which one goes to tensor core. So I think that's the second benefit of But in general, I feel like if you have rest pressure issues, observation works better, or maybe more complex code.
Okay, sounds good. So like, do you have like some? I actually missed the presentation. Do you have some real concrete numbers showing, for example, in certain hardware you are playing right now, how much you get, say, on flash attention, things like those complex kernel?
I think flash attention was around 20%. But then if we add computation pipeline plus ping pong stuff, I think it's getting closer to flash attention 3.
Oh, you mean Triton implementation?
Yes.
Get close to flash attention 3. Okay, good. Okay, thank you. That's perfect answer. Thank you. I do have the second one, is that we also like to understand the progress of the generic tensor descriptor programming. So this is not related to warp specialization, but it's a front-end programming. So last session, we have a presentation talk about the tensor descriptor programming. That one actually, kind of is not NVIDIA specific, like TMA, something like TMA tensor descriptor. It's a more generic. We really like to see that one going to more like official. But I understand that at the last presentation, people were still saying like a TMA tensor descriptor maybe still in certain area maybe still useful. I just want to understand the progress. Like how is this tensor descriptor programming make it more generic and make it more official? And yeah, I'm not sure that I'm not sure that
Yeah, I don't have a good answer, but I think TMA, the accelerator engine, is something is going to be more general over the hardwares. So on NVIDIA is there, on AMD, I'm not quite sure, but the new hardware may come with that. So it's something if we can generalize the fields.
Hello. Yeah.
Oh yeah, Phil. See.
Yeah.
Okay.
So I think the plan is for TMA, like tensor descriptors, to get out of experimental mode fairly soon, maybe like in the next few weeks, because I think at this point it's pretty final, the API, and also we'll probably add like a backward compatibility mode for it as well, so that it can run on GPUs that don't have TMAs. The caveat there is it will probably be slower than the tensor pointer versions, but yeah, plan is to make the tensor descriptors mainline and also deprecate the block pointer with this, because we think all the block pointer features will be covered by the tensor descriptors.
Okay, awesome. So basically, you're saying that TMA words were gone. We will stick to that more generic tensor descriptor.
Yeah.
Okay. Cool.
And also we also deprecate the host side tensor descriptors. So like currently, like in experimental namespace, we have like we still have one mode that allows you to create the descriptors on the host and pass them by value to the kernels.
Okay.
It does provide some minor performance benefits, like I think like maybe a few % or something at best for persistent kernels, and we'll deprecate that. So all the TMA code will need to use the device side descriptor API.
Awesome. So that will also allow user to auto tune it, I guess, because
yeah, that will be much easier to auto tune. It's possible otherwise, but it's very wobbly.
Sounds good. Yeah, thank you. That's all my questions.
We're looking for AMD because I know that AMD had some questions at one point. I'm sorry about that. I would like to get them to have a little bit of FaceTime if they would like to like video unmute yourself, and I will try to add you to the presentation. Looking around, don't see AMD unmuting themselves, so they might have like missed this meeting, or they might not have gotten like bumped out because we're using new StreamYard, and most likely we'll probably go back to using Google Meets, because it turns out we don't actually have to live stream this. So anyway, looking around the room, are there other topics that people wanted to bring up? We have still about like 14 minutes left. We might end up early if I don't have any other topics. Please put your other topics in the private chat, and I will bring you up. And I'll go take a look real quick right now while we have some time over at Slack to see if we have any questions in Slack. And I don't see any questions in Slack. All right. So, assuming that we have no more questions, and I don't know, I'm looking at Min Jiang right over here because Min Jiang has participated in these. Do we just end the meeting right now, or is there anything else? Okay, so we're going to end the meeting right now. We're going to give you back 14 minutes, 13 minutes. Go back to work. Enjoy yourselves. Thank you very much all for participating. And once again, you can check out the live stream on YouTube. It'll be permanent in a minute or two. Thanks. I will not use this tool.